Hello, welcome to my YouTube channel, Training Made Clear. Today's lesson will be Basic Electricity, Electronics, Part 1 of 3. Before we continue with the lesson, I just want to help you find all my other training videos. So type in Training Made Clear into the YouTube search bar. For my fun channel, type in Percy's Discoveries. Basic Electronics Training Module Introduction. Electronics is the study and application of devices that control the flow of electrical current. Understanding basic electronic components is essential for troubleshooting, maintenance, and circuit design. This module covers part 1 of 3 parts. In total, you'll be doing 18 different components. The first 6 is part 1 in yellow. The blue ones show part 2 up to 12, and then from 13 to 18, the green ones is part 3. Yeah, you can see all the different ones we'll be doing. The yellow ones, part 1. The blue ones is part 2. And the green ones is part 3. So in part 1, we're doing resistors, capacitors, diodes, Zener Diodes, transistors, and integrated circuits. Here are just some pictures of the components that you will be looking at throughout this course. So the first 6 that we'll be doing, you'll see the yellow ones, and then the other ones are blue and green. Here we have a picture of a resistor with its symbol. Resistors are the traffic cops of current. Function: a resistor is a passive electronic component that restricts the flow of electrical current in a circuit. They protect sensitive components from getting too much power and can be used to set specific voltage. The purpose: it's used to control voltage levels, limit current, and protect sensitive components from excessive current. Application: resistors are found in almost every electronic circuit in automation. They are often used in sensor circuits, timing circuits, and as part of voltage dividers to ensure the correct voltage is applied to certain parts of the system. Types of resistors are fixed resistors, variable resistors, potentiometers, and thermistors, which change resistance with temperature. Identification: resistors are identified by either color bands through hole resistors, printed values like power resistors, and numerical codes SMD resistors. The common resistor symbol is that little zigzag line there. And determining the color value for the 4-band color code. This is just a basic rundown. Band A is the first digit, and in this case it is brown, and the value is 1. Band B is the second digit, which is red, and you can see the next one is 0, which is brown, and then the tolerance. Polarity: resistors are not polarized. They can be installed in either direction. Both are correct. Example of a circuit, the LED current limiting. We have a 12 volt through a 600 ohm resistor to the LED to 0 volts. Without the resistor, the LED would burn out. Let's explain the 4-band color code in better detail. Here we have a resistor with the 4 different colors. Band A, the first digit. Band B, the second digit. Band C is the multiplier, and band D is the tolerance. Looking at the picture of the resistor on the right, we see it has 4 colored bands. Each band color has a value attached to it based on the table shown below. This is how to calculate the value of the resistor. Let's explain the 4-band color code in better detail. There's our resistor: blue, red, brown, and gold. Looking at this table that you see below here, you can see it has the value, then the color, and then a rhyme. We see band A is digit number 1, which is brown. Band B is digit number 2, which is red. Band C is the multiplier. This means how many zeros must be placed after digit 2. If it's brown, the value is 1 from the table below. So 1 0 will be after digit 2. Using the table below, we can calculate the value of the bands. So, as we showed above in red, blue, and green, we have the following. Digit 1 is brown, the value is 1. Digit 2 is red, the value is 2. Band C is brown, the value is 1. That means 1 0. Therefore, putting the values together, we have 1, 2, 0 ohms at 5% tolerance. Band D is the tolerance in gold, which is 5%. This band is not based on the color table below. Now, the color table that we see below, we have the values 0 to 9, and then we have under each value the color from black to white. And then we have a rhyme at the bottom which says, bad boys rape our young girls, but violet gives willingly. Notice that violet, above the violet, is a pretty lady. So that is the lady called Violet. So when we read this rhyme, bad boys rape our young girls, but violet gives willingly, it means Violet doesn't get raped, she gives herself to the men. Unfortunately, this is not a nice word to use under number 2, but this is how people have been taught this rhyme, and you can exchange that word for something better if you can think of something. But everybody has been taught this rhyme to learn the different colored bands. So it's a rhyme that is well known for helping people to remember the different resistor color codes. And I apologize for the choice of word used under value 2, but that's how the rhyme goes. So once again, there's our resistor. Here is the color-coded chart below. So on the previous slide, we calculated this resistor has a value to be 120 ohms. Now, if band C was green instead of brown, the multiplier would have been 5, because you can see green and 5 are together. This means there must be 5 zeros after the 12, which gives us 1,200,000 ohms, which is 1,200 kilo ohms or 1.2 mega ohms. This takes care of the meaning of the first 3 bands. Now, band D is equal to tolerance, which is different. Its colors are not in the table below. The colors for tolerance are brown, gold, and silver, with the tolerances of 1%, 5%, and 10%. The formula to calculate the tolerance is tolerance range equals rated resistance times tolerance percentage. So if a 220 ohm resistor has a silver band, 10%, the range is 220 times 0.10 or plus minus 22 ohms. The actual value would be between 198 and 242 ohms. If it was a brown band, the tolerance would be 1%, which would be 2.2 ohms. Right, looking at our color chart, the above rhyme is well known for helping to remember the resistor color code. While the above rhyme may help you immensely to remember the different colors of each code, there is always the confusion regarding 3 colors that start with the letters B. That is black, brown, and blue. My method to clear the confusion is to look at the opposite color of the last letter, which is white, and make that my first B, which is black. Now, there are still 2 B's left, brown and blue. So which one goes more with black? I would say brown, because it has 5 letters like black, and both words have a vowel in the middle, whereas blue has 4 letters and ends with a vowel. So I would say that brown should stand next to black. That sorts out the B's. Now, for the words with G, green and gray. My reasoning is green can look like blue, so it makes sense that the green should stand next to the blue. Gray is the closer color to black, and the white opposite was black. So the next closest opposite can be gray, and should stand next to the white. These are my methods to remember the colors. You can adopt this method if you want, or you can work out your own method. Before we move on to the next slide, I just want to go through this color chart for the resistors very carefully quickly. So just looking at the value and then the color and the rhyme. So the value 0. Underneath that value is the color black. And we use the word B for bad. Bad and black both start with a B. Then we go to number 1, which is the value, and the color there is brown. And we've used the next word as boys. And then on to number 2, which is red. The value of the red one is 2. And so we attach the word rape to that word. Number 3 is orange, and we use the word owl for orange. And yellow is number 4, and we use Y for young and Y for yellow. And so we go on right through to the very end. Now, V for violet, we've used it as a proper lady. Her name is Violet. So if you look at the rhyme, which says, bad boys rape our young girls, but Violet gives willingly. Violet would be the lady that we have in the little picture. So just saying that that rhyme, bad boys would mean black-brown. Rape owl would be red-orange. Yellow and green would be young girls. Blue-violet would be but violet. And gray-white would be gives willingly. So that's how we match up the letters. And the rhyme helps us to remember the colors of those different words. Now, so if I see, for instance, an orange color on a resistor, I would need to go to the orange word and look above it and see it's a 3. So if it's the first band, the first value would be 3. If the second band is yellow, I would go to number 4, so I would have 3, 4. Now, the next value is the one which gives us how many zeros we need to attach after the 3, 4. So if we have a color like brown, we would only have 1 0. If we have the color black, we'd have no zeros. So the value of that resistor would just be 34 ohms. But the moment I go to the orange, yellow, and then I go say brown, then I have 1 0 behind there, so it'll be 340 ohms. If it's a red color afterwards, it will be 3400. If it's say a white color afterwards, it would be 3, 4, and 9 zeros would be attached off that, which would mean it would be a very big resistor. Okay, so that's hopefully will allow you to remember this, why this color coding band and thing is there. All right, let's move on to the next slide, which is on capacitors. Capacitors, the little buckets of charge. Function: capacitors store and release energy, sort of like tiny rechargeable batteries. In some cases, they'll smooth out fluctuations in power supply and work as filters, while in others, they'll store up energy and then release it all at once. They are the component that lets your camera flash go off without frying the whole system. Charging of capacitors can be done with the help of an external battery. A capacitor only allows AC components to pass through it and blocks the DC component. Purpose: they are used for filtering energy, storage, and smoothing power supply in circuits. There's a picture of a capacitor. The application: in automation, capacitors are commonly found in motor start circuits, filtering noise in power supplies and stabilizing voltage levels. They also play a critical role in smoothing out voltage fluctuations in control systems. Some types, the most common ones, are electrolytic, which is polarized, ceramic, non-polarized, film capacitors. Identifying polarity: electrolytic capacitors have a negative stripe on the body, the longer lead is usually positive. Here we have a resultant wave output form on a charging circuit. This is like a battery charger. The rectification circuit would produce the resultant output waveform as shown by the dotted lines. So if you look at the dotted lines in the drawing, that's what the rectification would normally produce. Adding a capacitor would produce the waveform shown by the black line, the waveform with capacitor. This is the principle for a battery charger. See how much straighter that black line is compared to the up and down one. Diodes. The function. A diode allows electrical current to flow in one direction while blocking it in the reverse direction. Also reverse polarity protection. Also protects equipment if power is connected incorrectly. The purpose. Diodes are essential for rectification, converting alternating current AC into direct current DC, protecting circuits from voltage spikes and regulating voltage levels. There you can see the diode and its polarities. The application. In automation, diodes are used in power supplies, signal demodulation, and protection circuits. Example, flyback diodes for motors. They are also used in sensor interfaces to prevent damage from reverse current. Types: rectifier diodes, Zener diodes, and light-emitting diodes, LEDs. Polarity: the band marks the cathode, negative. Current flows: positive, which is the anode, through to the cathode, which is the negative. There you can see the symbol, and you can see what a diode looks like. Example circuit, a battery charger. That's our circuit below. Diodes D1, D2, D3, and D4 are in an arrangement to form a rectification circuit. This will cause an input AC current to output as a DC pulsating voltage. See the waveform without capacitor. Adding a capacitor results in a smoother DC voltage. See the waveform with capacitor. If you look at the bottom of that picture, you can see resultant output waveform. That's the one you should be looking at. Number 4, Zener diodes. That's a picture of a Zener diode, and you can see the black stripe shows negative. How a Zener diode works. In 12 easy to follow or easy to understand points. A Zener diode looks like a normal diode, but is specially designed to work in reverse bias. In a normal diode, current flows when the positive voltage is connected to the anode and the negative to the cathode. A Zener diode is usually connected the opposite way around, reverse biased. When the reversed voltage is low, almost no current flows through the Zener diode. Every Zener diode has a specific voltage rating called the Zener voltage, VZ, such as 5.1 volts, 6.8 volts, or 12 volts. When the reverse voltage is reached, the Zener voltage, the diode suddenly starts conducting current. Once it starts conducting, the voltage across the diode stays almost constant at its rated Zener voltage. Even if the supply voltage increases, the Zener diode will try to keep the voltage across itself at the same value. Because of this, Zener diodes are commonly used as voltage regulators and voltage references. A resistor is normally connected in series with the Zener diode to limit the current and prevent damage. If the current through the diode becomes too high, the diode can overheat and fail, so its power rating must not be exceeded. A simple way to think of a Zener diode is as an automatic pressure relief valve for voltage. When the voltage tries to rise above its rated value, the Zener opens and diverts current to keep the voltage stable. Here we have a circuit with a Zener diode in it. You can see RS above the Zener. The Zener diode keeps the output voltage approximately constant by conducting only the excess current required to maintain its Zener voltage. In your diagram, suppose the Zener voltage Vz is 5,1 volts. The supply Vz is 12 volts. The series resistor Rs drops the difference between the supply voltage and the Zener voltage. The load RL receives approximately 5,1 volts. The Zener diode also approximately 5,1 volts across it because it is connected in parallel with the load. What happens to the extra voltage? Not all of the excess voltage is dropped across the Zener diode. The excess voltage is mainly dropped across Rs. For example, supply voltage is 12 volts, Zener voltage is 5,1 volt. Voltage across Rs is 12 minus 5,1, which equals 6,9 volts. So the resistor drops 6,9 volts, not the Zener. What the Zener actually does, the current from the supply splits. Is is equal to IL plus Iz, where Is is the current through the Rs, IL is the current used by the load, Iz is the current flowing through the Zener. If the load suddenly uses less current, IL decreases, Iz increases, V out stays near 5,1 volt. If the load uses more current, IL increases, Iz decreases, V out still stays near 5,1 volts provided the Zener remains in regulation. Water pipe analogy. Think of Rs as a restriction in a water pipe and the Zener as an overflow drain. The resistor limits how much water can arrive. The load takes the water it needs. Any extra water is diverted through the overflow of the Zener to the 0 volt rail. The water level voltage remains constant. Transistors. We have the PNP and the NPN. Look at the drawing on the right. It shows NPN is not pointing in. It'll help you to remember it. Function. A transistor is a semiconductor device that can act as an electronic switch or amplifier. Purpose. It can control a large current or voltage with a smaller signal, making it fundamental in the switching and amplification of electrical signals. Application. In automation systems, transistors are used in switching circuits, signal amplification, motor control, and microcontroller interfaces. For instance, they control relays or drive motors by acting as a bridge between a low power control signal and a high power load. The types are bipolar junction transistors BJT and field effect transistors FET. Here we are shown an example of switching a lamp using a NPN transistor. We have 12 volts which goes to a lamp. From there it goes to the collector of the NPN and out of the NPN through the emitter and then off to the 0 volt rail. Applying current to the base will turn the lamp on. Transistors are constructed with silicon, which has been doped with either a positive substance, example aluminium, or a negative substance, example phosphorus. These can be sandwiched together as shown in the figure above, and the wires are connected as shown in the NPN type. The base is connected to the positive doped silicon, where the PNP type, the base is connected to the negative doped silicon. The entire construction of materials is encapsulated in a resin to protect the internal materials. Electrons flow from the emitter to base because a small voltage is injected by battery 1. The electrons only move from base to collector once battery 1 is over 0.7 volts. Then, because battery 2 voltage is much higher, the electrons move rapidly from base to collector. Two main types, bipolar and field effect. You can see there's a number on that transistor, and you can see the shape is also very important. When thinking about how a transistor works, Think about water flowing through a pipe that has a disc shut-off valve which can be opened by a swing gate. But the swing gate needs a reasonable amount of water pressure to open the disc valve. See Figure 1. Insufficient water on the swing gate to open the disc valve. Figure 2, the minimum amount of water is reached and the swing gate starts to open and some water now passes the disc valve. Figure 3, we have maximum flow causing the swing gate to open fully, which opens the disc valve fully for maximum flow to go through. Now imagine seeing the transistor connected to each pipe as in Figure 3. The collector is connected to the supply voltage, the emitter is connected to the outlet pipe, and the base is connected to the trigger swing gate pipe. To get the transmitter to turn on or switch, you need above 0.7 volts on the base for the transistor to put power out to the emitter. So we can see for the emitter to allow power to flow from the collector to the emitter, we need to have at least 0.7 volts on the base of the transistor or the full voltage of the collector. This base signal can be achieved from a switch to activate the transistor or a rise in volt from something like a solar panel. An NPN transistor starts turning on when the base is about 0.7 volts more positive than the emitter, and enough base current is supplied to drive the required collector current. Applying much more than about 5 volts directly between base and emitter can damage the transistor unless a resistor is used. The above circuit shows how a switch can be used to turn the transistor on. Replacing the switch with something like a solar panel, the transistor will switch when the base voltage is 0.7 volts higher than the emitter. NPN transistor. Current flows when the base is positive relative to the emitter. Examples: BC547, 2N2222, symbol, emitter, arrow out. PNP transistor. Current flows when the base is negative relative to the emitter. The examples are shown there. Symbol, emitter, is arrow in. Identification: read the part number on the package. Use a datasheet for pin arrangement. Note, in the NPN transistor, the emitter is connected to the negative side of the battery. Current combines in this transistor. The arrow on the emitter points direction of conventional current flow. Note, in the PNP transistor, the emitter is connected to the positive side of the battery. Current divides in this transistor. The diagram above shows how a transistor can amplify a signal. See, 1 milliamp out of the base can become 100 milliamps going to the collector. The ratio between these two is known as the current gain and uses the symbol beta. We are using a smaller voltage and current to control a larger voltage and current. When we input a small signal to the base pin, the transistor acts as an amplifier. We could connect a microphone which varies the voltage signal on the base pin, and this will amplify a speaker in the main circuit to form a basic amplifier. Summary. Modern electronics evolved from vacuum tubes, valves, to transistors and integrated circuits. The transistor became the building block of modern electronics because it provides the same switching and amplification functions as a valve while being much smaller, cooler, cheaper, and more reliable. Today, millions or even billions of transistors can be integrated into a single IC, forming the basis of computers, smartphones, industrial control systems, and communication equipment. Valves, more commonly known as vacuum tubes or thermomic valves, were the foundational electronic components used to control and amplify electrical signals before the invention of the transistor in 1947. Operating tubes in an audio power amplifier, the hot cathodes emitting their distinctive red-orange glow. Integrated circuits. Integrated circuits, ICs, miniature complete circuits made up of thousands or millions of tiny transistors and other components housed in a single chip. They serve as the brains of devices like microprocessors and timers. They contain many electronic components inside one package. It can include transistors, resistors, diodes, capacitors, all on a single silicon chip. The identification, you read the number on the that's printed on the top, as you can see in that picture below. If you look at this arrow that's flashing there, it's showing you a timer, the 555 timer, the LED flasher circuit. That's what we're seeing there. And that arrow is pointing to what's inside that timer on the left. So a practical example of combining components: a simple regulated power supply. You have the AC power supply, transformer, bridge diodes, capacitor, Zener regulator, transistor, and then the output. Let's just do a quick summary. If we look at the component functions, and just a summary of all of them that we've done: the resistors limit current, capacitors smooth DC voltage, diodes convert AC to DC, Zeners regulate voltage, transistors increase current capability, and ICs are precise regulation. If we look at polarities of these different devices, basically all you need to remember is that a resistor and a ceramic capacitor are not polarity sensitive, whereas all the others are. So you have to make sure, if you're using an electrolytic capacitor or a diode or a Zener diode, that you connect the polarity up correctly. And on ICs, certain power pins, you must have the correct voltage on there. These are the components that you've done in this course. So have a look at the pictures and remember what they look like. Now let's see how much you have learned by performing a test.